Okay, so definitely don't forget that. Really important for the final exam. In other announcements, homework 11 is due on Friday, so tomorrow by noon. And we're going to go over a couple of problems related to that. I'll give you some tips here in just a moment. And then, most importantly, our final exam Thursday. So Thursday from 10:15 to 12:15. Remember, I'll provide the equation sheet for that. And the exam, we have 120 minutes instead of 75, so you can expect it'll be a bit longer. The coverage is weighted more heavily on Chapter 7 than the other sections that you've already been tested on. And we're going to be doing kind of a sketch thing today, hydraulic grade lines, and I mean, I'm not making any promises, but for each of the last 5 semesters in a row, when I've taught fluid mechanics, there's been a hydraulic grade line sketch problem on the final exam. So the stuff that we're going to be going over today is pretty important. All right, where we left off last time was we were talking about local losses, sometimes called minor losses, and discussing the fact that it is the induction of turbulence that's responsible for losses of energy. So, for instance, a relatively abrupt change in flow direction is going to induce a separation zone where instead of having the same flow area that it did before, part of this, because of there's being a countercurrent flow, the effective flow area is reduced, where you can notice that the fluid is accelerating a bit because those streamlines are getting closer together. And so the turbulence combined with just less of an effective flow area reduces the pressure, and that's the manifestation of the loss in energy. And we've talked about K values and how they're proportional to the amount of energy that's lost, and the way that you use a K value is by multiplying it by the velocity head. But if you're trying to experimentally determine a K value, like you've already done last week in the lab, what we did was we looked at the change in pressure that was observed relative to the velocity head. So you can, as long as a K value is along, if you have multiple K values and at each of them the same velocity exists, you can add them together. But if you have K values at different points in a pipe network where maybe part of the pipe network is, for instance, 3 inches in diameter, other sections of the pipe network is 6 inches in diameter, the flow velocity would be different at each of those points. And so you would have to apply, you couldn't just simply add the K values all together. You'd have to multiply the K value by the velocity at the location where it occurs. So this summation term, you have to be careful about that. Only add together the K values that experiencing the same flow rate. And we've already looked at this table in the previous class, but what I wanted to point out here is some of the different valves. Globe valves, for instance, have a very high K value because of a very abrupt change in the flow location, as well as a reduction in the opening size for the flow. I thought that I had some pictures of globe valves. Let's just pull that up because it's interesting to look at. If we do a quick search, I think we'll be able to find a picture of a globe valve. The internal, this is a good one. Okay, so what it shows, bring that up a little bit larger. All right. So what you can see in this globe valve is that the water is flowing in from the left, and then it has to make a 90-degree change in direction, but consider the diameter of the pipe to the diameter of some of the internal parts inside of the valve. So this is a much smaller flow area, and particularly here where the water is coming up and then has to change direction again. The reason why we see such a large K value is effectively because we're forcing the water to flow through a narrower area. And anytime the velocity increases, then the head loss proportionally, well, not proportionally, exponentially increases, because head loss is a function of velocity squared. So whenever velocity increases, head losses are even more dramatic. So let's compare that globe valve to a gate valve. Okay, so a gate valve is going to cause much less of a disruption to flow. I guess probably the best way to show it here is this cutaway, because the gate valve just gets out of the way. The water flow isn't changing direction, and when the gate is up, so think about this gate is closed in this picture, but when it's all the way up, then the flow goes through the section unimpeded, and if anything, there's a little bit of extra flow area here. So it's still introducing a bit of turbulence because there's going to be water interacting with the gate that's up out of the way and down here at the bottom. But kind of the two extremes in terms of valves are the globe valve, where you maybe would see 10 times the velocity head being lost at that location, compared to a gate valve that's all the way open. 0.2 is the K value. So this is a wide open globe valve, and the amount of energy loss that's being experienced there is 50 times more than the gate valve. 50 times the energy loss. So it's pretty dramatic. In the expansion, you can apply K values there, determined by the relative ratio of the diameters, and in a pinch you can characterize the head loss just in terms of the change in velocity. This approach, though, doesn't take into account the taper of the transition, and so it's more accurate if you do have an idea of the angle of the taper here, to then use the K value that's calibrated to the rate of the transition. And you can see here that what our table suggests is that these K values are based on the velocity of the exit. So here where it says K sub E, then that would be the velocity of the exit flow. Okay, so that's it about local losses. On the homework, if you haven't already figured out problem 2, which is due tomorrow, I wanted to give you a hint on this. So you can see that we have the elevation of the water surface, the elevation of a fluid jet that's coming out, and of course the pressure of the water jet is going to be equal to 0 because it's surrounded on all sides by atmospheric pressure air, and so the pressure of the water at the surface is 0, the pressure of the water in the jet is 0, and the energy loss through this entire pipeline is defined as 0.152 meters of head per meter of pipe length. So you've got 35 meters of pipe length here, 3 meters of pipe length, and 5.5. So each one of those meters of length experiences a certain amount of head loss. And you're told to neglect the local losses, and so there's not going to be an entrance loss or a loss having to do with the bend here. But to determine the velocity in the pipe, you're going to apply the energy equation between 1, which is at the surface of the tank, and 2 will be at the jet. So the key to that problem is figuring out what to use as 0.1 and 0.2. And then the same thing is true for part B. To find the pressure inside the pipe, you're going to just have to think about where's location 1 and where's location 2. Once you know the velocity in the pipe, then you can choose location 1 to be the surface of the reservoir and location 2 to be T, or you could make T location 1 and the jet location 2. So either one of those will work, and you can get the answer both ways. Okay, so a couple of hints on problem 2, and then the other one I wanted to give you a bit of guidance on. We're going to look at a problem similar to this today, but the problem we're going to work today as an example has SI units rather than traditional units. And so here in the traditional units, what makes this a little bit tricky is it's asking you to determine the horsepower that has to be supplied to the water. So a horsepower is 550 foot-pounds per second. So if you look at the units that go into the power equation, If you're using traditional units, it's cubic feet per second as the flow rate. The unit weight will be pounds per cubic foot. And of course, for water, it's 62.4 pounds per cubic foot. And then H sub P is the pump head. And so the pump head is what you're going to be solving for when you use the energy equation. So here's location 1. Here's location 2. You think about all of the terms of the energy equation, including the losses, where you've got 2 sections of pipe. Fortunately for you, they both have the same diameter, which simplifies things a little bit. But you're going to be for 4 cubic feet per second, that will define what velocity has to be achieved. And so you're going to, from the 4 cubic feet per second in the given pipe diameter, then you'll put in feet per second into this equation for H sub F. And basically, you're going to solve for HP and then put that into the power equation. So the power equation will spit out foot-pounds per second, and then you divide by 550 to get horsepower. All right. Now, let's get that practice that I was mentioning. Here we have a reservoir that water is being pumped from up to an elevated location. Looks like this is a building on top of a hill, and we want to know what's the water pressure at the top of the building. So here at the top of the building, we have a given elevation, and what we're going to assume is that that the water is moving. And so here at location 1, the velocity is 0, but we are not going to neglect the velocity at location 2. So in the energy equation, V2 won't be canceled out because the pipeline continues. So we want 580 liters per second to go through this pipe network, and the length of the pipe is 2,000 meters. We've got the diameter, and then here's a formula that describes the energy loss due to pipe friction. So the entire 2,000 meter length is going to go into the L. And then we have a couple of K values that are specified. The K value of 1 is used when there's a pipe that projects into a tank rather than being flush with the edges, which would be 0.5. The K value is 1 if it goes into the tank. And then we have a couple of bends that are prior to the building. Okay, so part A is we're going to use the energy equation to solve for H sub P. And then we're going to apply those lessons about efficiency that we learned last time. And what we learned last time is that if you are generating power, you multiply by the efficiency factor. And if you're consuming power, then you divide by the efficiency factor. And then finally, let's take a look at what is the pressure at top of the building. And by the way, when you're applying the energy equation, it's this entire pipeline that is 2,000 meters. And you can see that at the end of the pipeline, the water is exiting as a jet. But for some reason, it would be, maybe there's another tank that is like below that. But the building itself is only 1,100 meters downstream. So it's 2,000 meters from tip to tip, but 1,100 meters is this intermediate location where the building is constructed, and we want to know the pressure at the top of the building. So we'll just be, once we have found the pump head that has to be added to the system, then we can again, in part C, use the water surface as location 1 and the building as location 2. In part A, we're going to have location 1 be the tank, and location 2 be where the water is exiting the pipe network. And the reason why we choose those two locations is because that's where we have the most information so far. That's where we know the elevation and the water pressure at both of those locations. And pretty easily we can find what's the velocity of the water at location 2. Because we already have a flow rate specified. We're trying to get the water to move at 580 liters per second. So with that flow rate, we can determine the velocity. All right, so we have some function that defines the friction losses, another that defines the local losses, and we know the length of the pipeline, the diameter of the pipe. Now, I also wrote it on the whiteboard, like which components of the energy equation can be canceled out. The pressure at 1 and the pressure at 2, because that's atmospheric. The velocity at 1, because it's a large tank where the water level, if it's falling, is falling very slowly, such that V1 is negligible. V2 is not canceled out because the water is flowing as a jet. So it's going to have a little bit of kinetic energy still, and we'll see the magnitude of that is relatively minor, but we'll keep track of it. There's no turbine, but there is a pump. So you can see that the H sub P term still exists because between 1 and 2 is a pump. All right, so here I've rearranged the energy equation to solve for our one unknown is how much energy does the pump need to add in order to achieve this flow rate. If it didn't add that energy, like if the pump wasn't there at all, then the water would not flow because its outlet is higher than the starting point. But if the outlet was lower, let's say that the elevation was 70 meters, as long as we primed that pump, it would begin flowing, even if the rest of the pipe went higher. So like, see how this, it says the elevation is 102. If we take this hose below the water level and then fill the pipe, it will begin to flow. And you can prove that to yourself. If you ever have to drain a swimming pool, you can do it without using a pump as long as you have some low point to have a hose go out. So my family had a pool when I was growing up, and it took a couple of days, but at the end of each summer we would drain the pool about halfway just by putting the entire hose in the pool, so filling it up and there's no bubbles, and then you'd kink one end of the hose and you'd take that end that is sealed by kinking it, you're just kind of folding it in half, and then you lift it up out of the water and make sure that it's not allowing air to get in the pipe, into the hose, and then you would carry that hose down the hill, and then you could open it. And as soon as you opened it, then the water would flow out, even though part of the hose went above the water surface and up a little bit of a hill before eventually going down a hill. And so as long as the downstream end is below the water surface, then it could flow without any pump. But that's not the case here. Here we have the outlet is above the water surface, and so that's going to necessitate this pump, both to overcome the elevation difference, but then also to overcome the effects of pipe friction and local losses. So let's consider the relative magnitude of those things. We're adding energy to overcome the elevation difference. We're adding energy because it was stationary and it's going to be moving. So this term is accounting for how much energy has to be added to get the water moving. And then we have our local losses and pipe friction. So I'm sure that you calculated the velocity using V is Q divided by A. So here our average velocity, 2.954 meters per second. So we can put that into the friction loss formula and find out that the amount of head that this pump has to add just to overcome the friction is 33.8 meters. So we're going to have to add as much pump head as the elevation difference plus a little more pump head to overcome this pipe friction, plus a little more head to overcome the local losses. Now compare the magnitude of those. 33.8 meters compared to 0.8 meters. And when you see the relative difference, that maybe gives you an idea of why they sometimes call local losses minor losses. Because compared to the effective pipe friction, usually fittings and valves and expansions are a much smaller piece of the pie. Okay, so altogether now, the pump head that has to be added is 50.44 meters. Did anybody get about that same value, 50 meters of head? Yeah? Maybe I didn't give you enough time for the calculations. So it's the elevation difference. Now look at the velocity head. Only 0.44 meters of energy is tied up in the velocity head. So that's relatively small, but not negligible. So as long as we're adding 50.44 meters, then we can achieve the desired flow rate. The desired flow rate that we want to be going through that pipe is 580 liters per second. So if our pump adds more head than that, what would happen? Well, the water would flow more quickly. If we can't get exactly the right pump, and if instead we had a pump that could only add maybe 48 meters of head, well, then what it would do is it would just pump at a slower flow rate. It would come into an equilibrium at whatever velocity equals the amount of energy that's left over to spend on overcoming the pipe friction. So it has to overcome the elevation difference. Even if we had a smaller pump, the elevation difference would still be the same. But the velocity it achieves would be lower because there just wouldn't be as much energy left over after accounting for the elevation difference to put into overcoming the pipe friction, the local losses, and this tiny little share that goes into the velocity head. So you can think of energy as currency. It's the energy that there is to overcome the hurdles of getting the water from the tank to this discharge. And the things that are those hurdles in the way are those local losses, the pipe friction, the elevation difference, and then the acceleration of the flow. So any questions on part A? Okay, so we've got the flow rate. I'm going to pause for a second and give you some time to calculate the power required. How much power, and I think I calculated this in terms of kilowatts because it's going to be quite a lot of energy. How many kilowatts is needed to get this motor and pump to add 50.44 meters? Okay, so it should be 495 kilowatts. Now think about, why is it that we're dividing by the efficiency factor if it is a pump? Well, it's because the amount of power that's required is going to be more if the pump is losing energy. Like if it was 100% efficient, you'd need to put in less energy than if it's not 100% efficient. So what's actually happening is that the pump is heating up and it's adding heat to the water. In addition to pumping it, it's adding a little bit of heat. That's where that other energy goes. And so if you don't divide by 0.58, what do you get? Something like 283 kilowatts, something like that. It's in the 200s if you ignored the efficiency factor. But since it's not perfectly efficient, you have to put in more energy than if it was. And so that's why you're dividing by the efficiency factor and not multiplying. And then the reverse is true in the case of a turbine. In the case of a turbine, you multiply by the efficiency factor because if a turbine was 100% efficient, you'd be able to extract more power than you can if it's not 100% efficient. So if a turbine is only, let's say, 75% efficient, you're going to get more energy out of that, you get less energy out of it than if it was 100% efficient. So you multiply by the efficiency factor to bring the number down lower. But in this case, it was a pump, so we're dividing by the efficiency factor, and it's just coincidental that the 0.58 is the same as the flow rate. In fact, I really need to change that example just to make the numbers different. So any questions so far on part B? Okay, now finally, we're going to look at this, this building on top of a hill. And we want to know what's the water pressure at the top of the building. So location 1 will be our reservoir, and location 2 will be the building where it's not the entire 2,000 meters. And so, before how we calculated the head loss, this was the head loss for 2,000 meters. Now you need to find a different head loss for just 1,100 meters because it's 1,100 meters downstream. The local losses is the same because all 3 of the local losses occurred prior to the building. But then the other difference is the elevation. Instead of 92.7, the elevation is higher, so that's going to affect the pressure as well. So solve for P2, where P2 is in that building. All right, so in part C, I've made a simplifying assumption that the water is flowing through the pipeline, and then the water comes into the building from like a secondary pipe. So you can see this thin black line that's going up to the top. And so what I'm assuming is that inside the building conditions are static, meaning that we're not currently drawing water through that pipe, and so that the velocity at location 2 at the top of the building is 0. But even if we don't have the velocity equal to 0, velocity head is relatively small. But I did want to just mention that for location 1 and location 2 both, I'm neglecting the velocity heads. Okay, so you can see that P1 and P1 is canceled out, V1 and V2, there's no turbine. So the modified friction losses are just going to be a function of the 1,100 meters instead of 2,000. So we're looking at 18.59 meters of head loss due to pipe friction. 0.8 still is the local losses, and the pump head that's being added was already determined to be 50.44 meters. So I ended up calculating that we should see a pressure of 55.5 kilopascals at that top of the building. And just in the spectrum of typical water network pressures, ordinarily about 240 kilopascals is considered a minimum. So I made a little note off to the side here is that that would be too low to provide adequate pressure, and during periods of peak demand it could even be the case that backflow occurs. And what backflow is if you open up the faucet and there's not enough pressure, actually sometimes air can get in and the water can be going the other direction. And that's an unsanitary condition because if you have sewage or just contaminated water, it can go into the pipe network the opposite direction if when you open the valve it's sucking water in. You always want your pipe network to be pressurized so that contaminants aren't working their way into the system. So about 56 kilopascals would be the pressure there. Now, so far on these examples, I've just been giving you some factor, like here it was 0.019. I've been giving you the friction factor. But in reality, the friction factor has to be calculated. And that's part of what we'll spend time in hydraulic engineering next spring talking about. We're going to be discussing the ways that you calculate the friction factor. And what makes this Darcy-Weisbach equation so much more accurate than the Hayes and Williams formula is that the friction factor changes depending on the flow conditions. And in fact, you can use a different friction factor depending on the temperature of the water and the diameter of the pipe. All of those things influence how rough the pipe effectively is and how much resistance it's going to impart on the water that's flowing through it. So one of the input parameters that determines what is the friction factor F is the material that the pipe is made out of. So there's this parameter epsilon. Some texts identify it as K sub S, but it is an equivalent sand roughness, which is basically, if you're to conceive of how rough that pipe is in terms of if it was spherical particles, what diameter would those particles be? So you can say, for example, if you have a concrete pipe that's rough, so think about the roughness of a concrete driveway. You know, you could make pipe out of that same material, and so the roughness excuse me, has the same effect as a surface that was spherical particles of 3 millimeters diameter. So you can see that cast iron is quite a bit smoother than that, and galvanized iron smoother still. Wrought iron or just steel pipe, quite a bit smoother. So there's these material properties that we can look up what a pipe is made out of. And it's hard to believe that there were ever pipes that were made out of wood wrapped in wire coil to kind of keep it all together. That just seems like it would leak. But in those days, wood stave pipe was a thing. There may still be a handful of places where it hasn't been replaced yet. Once you know the material that the pipe is made out of, and you also know the diameter of the pipe, then you can define where on the figure on this right side vertical axis to go. And so there's a relative roughness. And so, for example, if you were working with a cast iron pipe, so you can see from cast iron that the epsilon is 0.26. Let me just make some room on the whiteboard here. So what if we were talking about a cast iron pipe? Then the epsilon is 0.26 millimeters. And if the pipe diameter was 500 millimeters, then epsilon to D would be, let me just get my calculator out here. 0.26 divided by 500. Okay, it is 0.00052. So with that relative roughness, the equivalent sand roughness to the pipe diameter, you'd find some point on here. So 0.0005. So here is 0.0006. Here is 0.0004. So I'd be in between here. So between those two black lines. And then the next factor that determines what is your F value is what's the Reynolds number of the water that's flowing through the pipe. So you'd have to know the flow velocity. Remember that Reynolds number is the velocity of the pipe times the diameter of the pipe divided by the kinematic viscosity of the fluid. So you'd find the Reynolds number and you'd go up and you'd try and intercept the curve that you had defined before. So we have 0.005. So we would follow in between those two lines, and then we'd be intercepting a certain Reynolds number. And then once you intercept the Reynolds number and the curve, then you go over here to the left for the friction factor. So this is called a Moody diagram, and we'll spend some time in 331 next semester talking about and practicing the use of the Moody diagram to define the F value. So this is a lot more sophisticated than just having the same C value, the Hazen-Williams coefficient, that always applies regardless of what is the velocity, what is the temperature of the fluid, what is the pipe diameter. Those are all things that do dramatically affect how rough a pipe is and how much energy is going to be lost. And so this Moody diagram and the Darcy-Weisbach equation has the potential to be considerably more accurate. Now, we're going to finish today's class and the semester by talking about grade lines. This is just a way of graphing energy. And you've done this before already in the lab. You may remember from the Bernoulli equation lab that you graphed the hydraulic grade line and the energy grade line. So the energy grade line is a graph of the pressure head, elevation head, and velocity head. And in water that's not moving and in a tank, the energy grade line is just right at the surface of the water. And the same thing is true of the hydraulic grade line, because the hydraulic grade line is the pressure head and the elevation head. And so in a tank of water where it's not moving at all, there's not any velocity head, and so the EGL and the HGL are both at the water surface. But then think about what happens as the water flows from the tank into the pipe. So it's speeding up a little bit, and because of that transition from stationary to moving, now there's going to be a separation between the EGL and the HGL. Where previously they were both on top of each other, now, since there is some velocity, then the EGL will be higher than the HGL. So you can see that the label here is the energy grade line is the one on the top, the hydraulic grade line is the one on the bottom. And this image is depicting that if you were going to put a piezometer tube, connect it to a pipe, that the water level rises to the location that coincides with the HGL. But if you had a piezometer that was actually intercepting the flow with a stagnation tube, so I guess this is maybe a little bit like a pitot tube. Remember how we talked about pitot tubes earlier in the semester? So it's facing and intercepting the water. It reaches a point of stagnation and it pushes the water up a little bit higher than it otherwise would if it was just connected to the side of the pipe. Because when it's connected to the side of the pipe, it's not capturing the velocity head. But this second one is capturing the velocity head, and that's why it pushes it a little bit higher. But both of these are sloping downward, because the further along you get in the pipe, the pressure is decreasing due to pipe friction. So the slope of this line reflects the rate of energy loss due to pipe friction. But you'll notice that the EGL and the HGL are parallel to each other. So that's a key characteristic, is that they're parallel. And the reason why they're parallel is because the velocity is not changing. As the water goes through the pipe, the velocity is constant. And so the deflection, how much difference there is between the EGL and the HGL, stays the same as long as the velocity head isn't changing. And then finally, here at the outlet, the EGL is a little bit above the water surface, because as the water is flowing out, it's a jet. It doesn't have pressure anymore, but it still has some velocity. And so the EGL is above the free surface of the jet that's coming out of that pipe. So these graphs of energy can be useful in the design of water networks and water treatment plants, because oftentimes what you're trying to do is reduce how many pumps you have to have in a treatment plant, and you're trying to use gravity flow as much as possible. And I've seen treatment plants back in the western United States where the water's coming from the mountains, and so they'd have to use very few, if any, pumps, because they're just able to have the pressure of the water flowing downhill kind of drive the treatment process. And so if you have in your design plans for a treatment plant, if you're sketching out where is the energy grade line and the hydraulic grade line, then you can see basically a visual reflection of how much pressure is in the water and how much energy there is to continue to drive the flow through the system. Now, here's what happens to the EGL and the HGL when there's a pump. Remember, what a pump does is it adds pressure. the effect of the pump is that water flows more quickly than it would if the pump wasn't turned on. But compared to the inlet and the outlet pipe, if the diameter of those two pipes is the same, the velocity in and the velocity out is the same for a liquid, because liquids are incompressible. So a pump is not speeding up the flow of the outlet compared to the inlet. A pump is speeding up the flow compared to if there was no pump there at all, but velocity in and velocity out's the same. So some of the things that's important to notice about this figure is that look at the slope. The slope of the EGL and the HGL is the same before and after the pump, because the slope of this line reflects the rate of energy loss due to pipe friction. And we have two pipes that are the same in and out of the pump. But what the pump does is it adds an immediate increase in energy in the form of additional pressure. So this is a vertical line. This line isn't slanted. This is a vertical line because it's instantaneously increasing the pressure. And then the water continues to flow in the downstream direction, and so therefore there will be energy losses. Therefore the pressure is continuing to get lower in the direction of flow. Here's what happens with the turbine. A turbine extracts pressure. So you can see that we have some downward sloping EGL and HGL because of the pipe friction, but then a huge loss in energy where the turbine is taking out energy. And then, this is kind of a little bit obscure, but look at the outlet coming out of the pump. This is a pipe where the diameter is increasing, and so the EGL and HGL are getting closer together. As the velocity gets smaller, then the relative difference between the energy grade line and the hydraulic grade line, it's getting closer together because the velocity head is smaller as the velocity itself decreases. In a nozzle is that effect that I've just been talking about, but in reverse. So in a nozzle, velocity is increasing as the diameter is tapering inward, and so the velocity of the water goes up, the velocity head, the difference between EGL and HGL is getting further apart. And you can see as soon as the water comes out and is jetting out from the nozzle, then the HGL is in the water itself because there's no pressure. And remember, HGL is elevation plus pressure head. But the EGL is above it in the amount of the velocity head. This is what happens when the pipe diameter is reduced. A reduction in the pipe diameter, this was a big pipe with a large diameter, and so therefore a relatively lower velocity. So the water's moving slowly in the big pipe, and it's moving faster in the small pipe. And so it's moving slow. The slope of the EGL and the HGL is less compared to when it's steep. The slope of the EGL and the HGL is steeper because you have faster moving velocity and a higher rate of energy loss. And also the distance between those two is larger because the distance between the two lines, the EGL and the HGL, is a function of the velocity head. So if you have more velocity, then you've got more velocity head. The water's coming from a tank and it's discharging into a tank. And when that happens, the HGL ends at the water surface, but the EGL is above it because you're losing some energy, you're losing the velocity head as the water comes into the tank. Now this is that case I kind of talked about before, that it doesn't matter how high a pipe gets, it only really matters where is the outlet of the pipe. So the pipe can go above the EGL and the HGL, and if it does, then this is going to be a location where the fluid pressure is actually negative. So if we punctured the pipe at this location where it's above the EGL and the HGL, if we poked a hole in the pipe, it would actually be sucking air in rather than having water jet out. But any place that you would puncture the pipe below the HGL, then the water would flow out. But above the HGL, the pressure is negative. So you'll notice here that they're measuring the location of the pipe either above or below the HGL to indicate whether the pressure is positive or negative. This is that example of emptying the swimming pool at the end of the season that I was talking about, where I could have my hose go up over a hill as long as the downstream end was lower than the elevation of the water inside the pool. Okay, so the key things to keep in mind when you're sketching an EGL and an HGL, the key attributes is that first of all, it starts at the water surface in a tank, then the two diverge because as the water begins to move through the pipe, there is now going to be velocity head. And how far apart these two lines are is a function of v squared divided by 2g. And the two are parallel for a pipe that is constant in diameter. The slope of the line reflects the rate of pressure loss, and you should have, when the water discharges at a jet, you should have the line of the HGL terminate at the jet itself. I don't know why they were a little sloppy here, and you see how they've got it terminating before the pipe? It would be better if they had that actually ending at the water itself. But remember, the pump immediately adds pressure, so that's a vertical line upward. Now I've got a handout for you to practice sketching these yourself. Let me hand this out to you. So as you do this, I suggest using a pencil. You may need to come back and make some corrections later. And if so, I've got a couple of extra handouts. But try and sketch where you think the EGL and the HGL would be for this figure. And there's one on the back as well. So this is front and back. A thin line represents a smaller pipe than a thick line. So thin line is small diameter pipe where the velocity would be moving faster, and a thick line is a large diameter pipe where the fluid velocity would be moving slower. Okay, so the first one, some of the characteristics that this ought to have is that, of course, the EGL and the HGL starts at the water surface, but then they diverge from each other. The EGL is the one on top. You need to label it. The HGL is the one on the bottom. They're supposed to be parallel. It looks like maybe I'm a little bit off with that. But you have the smaller diameter pipe, means that the water is going to be moving at a faster velocity. So this part of it is steeper than the other one. So the other one, the HGL, should terminate at the water surface, whereas the EGL is a little bit above it. And then the slope isn't as steep for the large diameter pipe because the velocity is slower and the two lines are closer together. So those are some of the main characteristics. There's also this immediate downward drop in both of them, And that's because what I'm assuming is that there's a local loss at the expansion. And so we don't know how big the magnitude of that local loss is, but the main things that you ought to be showing here is that when the water is moving faster, the slope is greater, and then the larger deflection for the faster moving flow. Okay, now the other one looks like this. There's a pump. In the sketch that I gave you, the water flow is going from the left towards the right, and so that makes this a pump because it's clear that the elevation of the water is greater on the right. So in order to get the water to flow, here's our small diameter pipe, which means that the velocity is relatively faster. So there's a larger deflection between the EGL and the HGL. It's steeper. And then we have this straight line up for the pump, and then it's going downhill again. And the HGL stops at the water surface, the EGL a little bit above it. But it shouldn't be as steep because the diameter of the pipe is larger. All right, 12:14, that's all for today. I'll see you for our final exam, which, as a reminder, is scheduled for Thursday. And of course, the homework's due tomorrow by noon.